20 by 20 or something. But you sort of imagine that's just not going to be powerful enough to learn anything truly complex. So the more dimensions you give it, the more it has to work with and can figure out. So that's probably where I'd start. Just make it bigger. Introduce more parameters. In general, in machine learning, more parameters equals more sort of ability. A more complex hypothesis base. Okay, other questions? Yeah?
I don't know if you're aware of this, but currently the link to download text files
Oh yeah,
broken.
somebody said that. I
It's on
assumed the TA.
someone posted it in there. But I just tried like an hour ago.
Oh, okay.
So Greg fixed it. Like if you look at the imports now, there's like a WK import and just grabs the text file.
Okay, Greg fixed it. Okay, well, I see. The code is okay, but the link is still broken? Okay. TAs.
So I tried a lot of different things, and the link never worked.
Oh,
It's on Piazza. Just go to that question. The text files are there. Sorry.
Oh, wow, okay. Well, I'll see. It sounds like we need the big guns. So I'll go ahead and I'll look at it. Okay, give me a PhD in computer science. Fix the download link. All right. Luckily, we have one. Okay. Any other questions? Yeah.
I just want to double check. We're doing it fixes character by character.
Character by character.
And so it's not the encoder, RNN, decoder.
Right. We're not doing encoder decoder stuff.
Okay.
So it's just a little recurrent net. Character comes in, character gets spit out. Yep. Yeah. We'll worry about encoder decoder stuff a little later in the semester.
I was wondering if there's a reason why the encoder decoder tutorial was linked as like required reading for the lab. So I feel like that was a little misleading.
Oh, yeah. I mean, it's just to help you understand and sort of see how all the pieces fit together. We didn't want to make you do a full encoder decoder. We wanted something much simpler. So this is just supposed to be the most basic RNN that does something interesting. Yeah, correct.
Are we supposed to implement a GRU, or are we just supposed to use the NN GRU?
So I would recommend using the NNGRU to begin with, just to debug your code. But then as part of the lab spec, you are required to implement your own GRU cell. Which is, in our last lecture, there was a slide where we showed the 6 equations that should roughly translate to 6 lines of 5.5 code for you.
When are you going to post those slides?
Oh, are they not posted?
No.
Oh, I'm so sorry. I will post them right after class. Let me make a note of that. Hold on. I'm going to test myself. Let's see here. I should probably have a better way. If I had a pen, I could write this down. Okay. Post notes. Great, now I have it. Okay. All right, any other questions before we move on? Okay, then what I'd like to do is tell you about ResNets. So this is a very simple idea, and you're going to be surprised when we get there. You're going to say, wait, Dr. Wingate, that's it? That's a very simple idea. I'm going to say, yeah, it's amazing what a difference this very simple idea makes. So I found these slides. This is actually slides from a guy named Kai-Ming He. This is the same key of Xavier/He initialization. So this guy's the guy that came up with all that initialization stuff that you use. So he sort of made this breakthrough in neural net topology design when he invented this thing called a ResNet, or a residual network. And just to put this in context, when deep neural nets started to become useful, way back when neural nets were first invented, people would do like 2-layer nets or maybe 3-layer nets. And then right around 2012, people started figuring out some stuff, and nets got much deeper. Maybe 6 layers or 7 layers, or maybe like 10 layers. It wasn't until the advent of some of the concepts behind ResNets where all of a sudden you could build networks that were 1,000 layers deep. And so you can imagine what 1,000 deep network, like what is the problem with that going to be? Vanishing/exploding gradients, right? So you might be wondering, like, wow, okay, so if you have 1,000 layers, what does that tell you about the Jacobian of each layer, roughly speaking? So can the Jacobian make gradients bigger at every layer? 'Cause what would happen if it got bigger 1,000 times? It would explode. And can the Jacobian make things smaller as the gradients go backwards? No, because what happens? So what must the Jacobian be doing? It must be essentially constant. So the Jacobian must be not close to 1, but actually 1. And the idea of a deep ResNet is here's a way to construct a network such that the Jacobian of a layer is exactly 1. And what that means is that gradient information can flow freely from many, many, many layers, thousands of layers. So I want to take you through his slides because I feel like I didn't really want to reinvent these slides. So we're going to shamelessly borrow his slides. So there's going to be a few slides that we don't need, but we'll sort of just go through them and talk through them. So by the way, the story here is very funny. Remind me to tell you the story of how these were invented if I don't get to it. Okay, so just sort of again to motivate this, when he first came out with this back in a couple years ago, 2 years ago, in 2016, when he when ResNets burst onto the scene of deep learning, it dominated all of the competitions at the time. So 152 layer network was the thing that won the ImageNet classification in this 2015 competition. Detection, ImageNet localization. So not only was it first place in essentially every category of every competition that was held, it was quite a bit better than anything else. So this represented a real advance in terms of the state of the art of networks. And here you can sort of see, I think this is really interesting. What they've done here is they've said, let's look at performance on, in this case, an ImageNet classification task as a function of depth. So back in 2010, when we first got going on ImageNet classification, error rates were something like 28.2, and the networks were shallow, maybe 2 or 3 layers. And then in 2012, we got up to 8 layers, and that's when deep nets really started taking off. And then 19, and then 22, and then all of a sudden, 152. And that has given us the very best classification accuracy that we have. And then here you can sort of see like a schematic comparison of what that looks like in terms of a computation graph. So VGG, this is the VGG net that you know and love, from style transfer, all 12 layers of it. And so putting the 152 layer ResNet to the side of that, I think really emphasizes just how deep these things are. Same thing is true of other tasks. We can skip all this. Okay. So we know all of this stuff. I want to get to, let's see, we know about this, we know about patch norm. Here we go. Okay. So there's this very interesting question that he raises in his slides, which I really like. He says, okay, let's suppose that I'm an image classification guy, and I see the results of some guy, and he's trained his 12-layer neural net, and I think, okay, I want to do better. So can I do better if I just make my network deeper? What do you think?
No, because that person would have.
Okay, so you're like, haha, trick question. Clearly the answer must be no. Okay, so why? Why doesn't making things deeper mean that performance improves? What's the intuitive reason for that? Okay, so what's the counter argument? You might think that deeper networks should result in better performance. But up until this point, that wasn't true. So why would you think that they would result in better performance, first of all?
More parameters.
More parameters. And more parameters means more complex hypothesis space, more nonlinearity, better function approximation, everything. So you might think, if I'm adding parameters to a model, that it's got more capacity to learn. I should be able to at least memorize more data. But you can't. Why not?
It's harder for each parameter to learn.
Right. It's not trainable. So adding parameters doesn't matter if you can't train those parameters. Right? So I just want this to be clear in your minds. So up until this point, it wasn't the case that you could just stack things arbitrarily deep and sort of see performance improve as a function of the number of parameters. And the reason is because they weren't trainable. And why weren't they trainable? Well, things like vanishing and exploding grid. So here's a graph showing this. Okay, so this is sort of a quantitative version of this same argument. So let's see if we can unpack what's going on here. So here's a network that's been trained on CIFAR-10. So this is little 32 by 32 images, 10 class classification problem. Here's iterations, and here's performance, percent train error. And green line is a 20-layer network. And after 60,000 iterations, you achieve some accuracy level. But a 56-layer network, more parameters, deeper, ends up much higher. Okay, so this is like the quantitative version of that same story I'm telling you. So not only does it not get as good on the training set, what does test set error tell you as well? It's also, like, it doesn't generalize as well either. So not only are you not doing as well on the training set, you're not doing as well on the test set. Okay, so you can't drive the error lower. It doesn't generalize as well. Like this thing, even though it has more parameters, it should be better, is not trainable. Okay, let's see if we can interpret this slide. So, what do you see here? So, someone talk me through this left-hand side in English. What's going on?
More layers is less is more error.
More layers means more error. So it's like, in fact, so it's like, not only is it like it's monotonic. It's like the more layers you put on, the worse you're getting. It's not like even you just do as good as a smaller network. Like you can't train it at all. The more you try, the worse you're going to do. Okay, and then you might think, well, maybe that's just CIFAR-10. By the way, that's true of training set error as well as test set error. You might think, well, maybe that's true just of CIFAR-10, but it's actually the same story on ImageNet 1000. Okay, this is like a well-known fact. So how do you get? This is a great slide. Sorry. Okay, so here's an interesting experiment that they did. So on the left, you have a shallow model, 18 layers, which we've shown here has better accuracy than all the rest of these. Okay? So they take this 18-layer model, and they introduce new layers, and they copy all of the trained parameters from this shallow net over to here, and then they make sure that they initialize all of these convolutions such that they're set as an identity function. Okay, so by construction, this network should have the same, initially, should be exactly the same as this. So we've essentially we're initializing this network in a really good spot. Is that clear? Okay. And so now, what happens? Now we can take this new network, which has been initialized to be exactly equal to this 18-layer network, and we can begin to try to optimize it. And what we find is that even if you do this, the optimizers can't do it. They can't do any better. So even though you've added parameters, you've initialized carefully, you can't seem to improve generalization accuracy. Okay, so what's the solution? The solution is something called a ResNet. So how does it work? Okay, so here's a normal network. You have an input, goes through some weight layer, maybe a ReLU, some other weight layer, ReLU, etc. And you can imagine that the results of this little chunk of network is just some nonlinear function we'll call h. So x comes in, h of x comes out. Okay? The idea behind a ResNet is very, very simple, and this is it. So what you do is you take x, and you just have x skip down to here. And then you pass x through this thing, and then we'll call that f. And you set the final output of this entire thing to be the nonlinear bit plus the identity bit. And that's it. That's a ResNet. Okay, so ask some questions. Go.
Is this similar to what we did for a unit?
Sort of. So in a UNet, we sort of did this. We concatenated stuff. But yes, we had stuff that we just sort of copied over. And that is kind of like what's going on here. And that's part of the reason why the UNets tended to be very trainable. Okay? Okay, so just make sure we understand. What happens if you initialize the weights of this little block to all zeros? What happens? What? You just get the identity. So if you initialize everything to 0, x just goes through and x doesn't change. And so what does the Jacobian of that look like? It's 1. Right? So there's this identity path that goes through the network where x is just, and then what we're going to do is we're going to stack these on top of each other. So there's this identity path where x is just going to get passed from layer to layer to layer to layer. And then all this nonlinear bit has to do, so if we want to learn the identity mapping, it's actually quite easy. We just set all the parameters to 0. But if we want to model something, then all we have to do is model what's called the residual. So the bit that's not the identity mapping. And that's why it's called a residual network. So these weights in these layers, all they have to do is model the difference between what x was and what you wanted somebody downstream wants it to be. Go ahead.
What happens if x is a tensor with different dimensions than f of x?
Yeah, so we still have to do something, so first of all, you don't do that. So x is going to, so the question was, what happens if x is a tensor that has different dimensions than f of x? And in ResNets, you don't do that. There will be times when we have to change dimension, and so we will every now and then introduce layers that will like squeeze or shrink x, and those are not quite like this, but we'll get there in just a second. Okay, so again, if the identity was optimal, very easy to get to, you just set all the weights to 0. By the way, that's what your regularizer, if you had weight regularization, would probably be doing anyway. And if the optimal solution is close to the identity, that's great. All you have to do is like small fluctuations in these weights, and actually the identity path is going to take care of most of the heavy lifting for you. So contrast that, again, with this. If you want to learn the identity mapping here, what should you initialize your weights to? Like, I don't know. Like, it's going to be something crazy because you have ReLUs in there. Okay, so here's the test. We've got 2 networks here, a plain net, which has 20 or so layers, and then we have the ResNet. And hopefully you can sort of see what this picture is. So you have 7x7 convolution with 64 filters and stride by 2, and then a pooling layer. And then from then on out, you have these residual blocks. And then every now and then you change sizes. So we have a bunch of 64 filter banks, and then a bunch of 128s, and then 256s, and then 512s, and then average, fully connected, and output. Okay, so 2 networks, exactly the same. Now, let me ask you another question. How many parameters do we have here? I don't know, n. Let's call it n. N parameters here. How many parameters do we have here? Also n. So it's the same number of parameters here as here, assuming that things don't change sizes. But we're using those parameters in a slightly different way. This is called a reparameterization. So when we think about these 2 networks, how many parameters does the left one have? I don't know, n. How many does the right one have? Also n. Okay, so it's the same number of parameters, and it's the same depth, and it's the same blocks. All we're doing is adding these little skip connections. Okay, then there's nothing else going on here. There's no like hidden things or dropout or anything like that. So let's see what happens. Okay, so plain net on the left. What happens as you make it deeper? Worse. Strictly worse. ResNet on the right, same data set. What happens as you make it deeper? Better. Strictly better. Same net, same number of parameters, same topology. All you've done is change these little residual connections. So this is like a huge breakthrough, because what this says is if you're just a little bit thoughtful about your topology design, you can go from networks that get more and more untrainable to networks that are trainable no matter how deep, essentially, no matter how deep they go. Okay, go ahead.
So it's not like the further deep you go, the bigger the skip connections need to be?
Right,
They're only like, they only need to be every 2.
right? I mean,
Or like,
once you are armed with the power of a skip connection, you can start sticking skip connections anywhere you want. but the point is, I think this is great science. Like, this is a very clean illustration of the power of these very simple idea. Okay, keep going.
Is the only reason why we don't do it any more than like 100? Is that because it gets too big and the model is too
So there are computational issues when you start trying to train a 1,000-layer neural net. Although they did do it somewhere in here. Let's see here. Oh yeah. Right. Well, they end up talking about. Yeah. Hold on. Let's see. We're gonna go through all this in just a second. They eventually get down here to 1,000-layer networks that are trainable. So we can get there. Just have to be a little careful. And we're going to go through sort of some of the math here so that we understand what it takes to get to 1,000 layers. Okay, yeah.
So then, I guess my question would be, why do you have to have multiple skip connections? Why couldn't you just have one skip connection that provided that identity path that you need to keep the Jacobian 1?
So you're saying, why not just have something from here all the way down to here?
Yeah.
Yeah, so I think what this is saying, what we're trying to avoid is lots of nonlinear things stacked together. If you had one giant skip connection, then yeah, you'd have an identity path and you'd be trying to model the residual. But essentially that would be like trying to model everything with the residual. This topology says at every step I only need to model a little bit of residual, and then I add it in, and model a little bit more and add it in, model it a little bit more, add it in.
So like maybe somewhere in within that giant skip connection, it could have the Jacobian would be 1 over the whole thing, but there could be parts of it where gradients disappear and blow up.
Yes. Right, so whereas here, locally at any point, you can kind of imagine that if the network decides that some layer it doesn't want, it can like just zero out. It can just zero those blocks out and things will just route around it and it'll be fine. Whereas that wouldn't happen if you had one gigantic. So you could imagine that there's lots of emergent properties that this could have. It could automatically tune the number of layers that it has if it decides that's what it wants to do.
What are these different colors? So
The colors are only showing the size of the filter banks involved.
so they're all convolutional.
Everything's convolutional. Yep, 3x3 convolutions. So this is 64, this is 128, 256, and then 512.
For the dotted lines, when they change the
Yeah.
size of those banks, how
Yeah.
do they like stack?
Yeah, I think they do some sort of stacking and reshaping. I don't remember the exact details, but it's just like the obvious thing that you do. Yes.
This kind of feels like the long short-term memory thing to me, because with the like normal stuff, it's really hard to just hold on to stuff that you want to keep, whereas this it can hold on to stuff that it wants to keep.
Yes.
A lot more easily.
Yes, and in fact, when we go back, we're going to look at LSTMs again, now that we understand this, and we'll see that the long-term memory path looks like ResNet, just horizontally instead of vertically. Yeah.
Why 2 layers?
Why 2 layers? Why not more?
Or less? Or less?
Okay, so this is the way they've designed this block is just about the smallest possible thing that makes sense. So there's some weights, a ReLU, and some weights. Notice that there's not another ReLU here. So why do you want this weight layer here? Why not just have weights and a ReLU?
Oppose the nonlinearity, or more nonlinearity,
Well,
or like,
I think there's a more basic reason.
So this is a guess, but I'm thinking that the ReLU is a nonlinearity that changes things for the first weights, but now you're adding the identity to what comes out of the second weights, and you want that to be affecting how the weights change in this layer.
Mm, maybe. I think it's actually something even more basic.
So the value only gives you 0, it only gives you positive numbers.
It only gives you positive numbers. And so you can sort of imagine that, I don't know, like if I start with some positive data and like my output needs negative data, if I didn't have this weight layer here, there'd actually be no way to get that. You have to have, so you want each layer to have, there's a little bit of linear, a little bit of nonlinear, and then this, I think, just basically gives you positive and negative stuff. So you can't, I don't think you can reasonably go much smaller than this.
But if we're putting the ReLU after the sum, doesn't that make it so the identity doesn't go all the way back because it has this nonlinear activation between every identity skip?
Oh, this ReLU here?
Yeah.
I'm actually not sure why that says ReLU, because I don't think that's what it actually does. I don't think that exists. I'm not. Well, maybe it does. Actually, we'll see some ablation tests a little bit later. Well, they're going to go through and they're going to do a lot of variations on this, and we'll see that. They tried many different reasonable variations on this, and this is the thing that works the best. Yeah.
So why not more layers?
So why not make this bigger? And again, I think that's just because this is the most minimal, simplest thing that works. I think in practice they do stick like a batch norm in here, and maybe like a little dropout thing. Okay, so let's keep going. So training on CIFR 10, we see the simple addition of these resonant connections totally changes the trainability of the network. More layers are now more trainable, they give you more performance, things are behaving as they should. That's true not just of CIFR 10, but also of ResNet, of ImageNet. So here we have 34 layer, 18 layers, so on plain networks, more layers is worse. But on exactly the same size ResNet, more layers is better. And not only is it better, it's like, so the 34 network is, so both the 18 and the 34, I think, just barely, but I think, get better both test and training set accuracies. Yes. Interestingly enough, you can see the dashed line here. So training accuracy is going quite a bit lower. Test set accuracy is just lower. Okay, so so you can also imagine some variations of this. So this is what we just saw, maybe a 3x3 convolution with 64 filters, ReLU, gives us sort of this basic block. But you could imagine doing a little bottlenecky sort of thing, like a 1x1 convolution sort of thing, et cetera. So actually, I think we're going to skip this slide. Hold on.
Question?
Yeah.
Is there ever a time when it's worse to do ResNet? Like, can you do it like a 4 or 5 layer? Because this is just for. Is it ever a bad idea?
I think it's pretty rare that ResNet. Like in some ways, I feel like I should teach this class the other way. Like we should just start with ResNets. like why even teach you convolutions without ResNets? Like that's essentially like no one should ever start there. You should just start here and only not do it if you have a good reason not to do it. In my opinion. Okay, so so by the way, interesting facts here. So this is ResNet performance on this is what is this? This is ImageNet. As a function of depth, so more layers means better performance. And then there's this little note that Kaiming makes. This model, 152 layers, has lower time complexity than the 16-layer VGG net. So it's actually faster. And the reason for that is the power of small convolutions. You have lots of small convolutions. So it's a simpler network, it's faster, it's deeper, but it performs better, which I think is pretty cool. Then we saw this already. Okay, so I think I think this raises some interesting questions, and Kaiming summarizes them here as these 3 things to think about when we're considering a model. There's the representation ability, and we've discussed this in terms of the number of parameters. If you have more parameters, you should be able to represent more. But then there's the optimization ability. So is it feasible to find an optimum if I have many more parameters? Not all models are equally easy to optimize, I think is a great way to summarize that. And then there's this other question of generalization ability. So once you've found an optimum, how well does it perform in terms of generalization? And we can evaluate topologies on all of these dimensions, and it's important to think about all of them in concert. So how do ResNets sort of impact all of these? Well, in terms of representation, it allows us to go deeper. That means we are able to introduce more parameters, and that means that hopefully we're able to represent more complex things. Optimization is changed because of this identity path through the network, which keeps Jacobians near unity. And then generalization ability, this is a more ad hoc argument, but conventional wisdom in deep learning is that deeper is better. That in general, the deeper you can go, the more abstract kinds of representations you're going to be able to learn, and that those will hopefully carve the world at its joints and generalize in a proper way. There's no formal statement of that, but only a lot of empirical evidence. Okay, so let's talk about this identity a little bit more. So here's their model. Okay, so this is, that's right. I'm so sorry. I may have led you astray. So originally they had, sorry. The original ResNet was something like, you have the input, you have the identity over here, you have the nonlinear bit here, and then we had that ReLU. You were asking about that. I said I thought that was a mistake. Actually, maybe it's not a mistake. I'm remembering that. So you can imagine that this overall thing, there's some function at the end, which in our original case was a ReLU. And so they're saying, well, what if that function was just the identity? In other words, what if we got rid of the ReLU? So it just looks like this. And let's see, so there was, shoot, I wanted to know. Yes, this was it, okay. Yeah, I'm sorry, I wasn't prepared. I thought I was prepared to talk about this, and I'm not. I wanted to go to this experiment. Okay, because I think this tells us what we want to know. Okay, so let's see if we can parse this slide. So we're looking at 110 layer ResNet on CIFAR 10, so we're doing image classification. Here's the original model. 3x3 convolution, ReLU, convolution, addition, ReLU. Here's the error that you get. Now, the question that maybe you all ask is, well, what if this was deeper? What if it was more complicated? What if we did something else? So here's a bunch of variations. And so let's see if we can go through them and find out what's going on. So what about this one? So this is called the constant scaling model, where we take this bit and we take this bit, and we multiply both of them by 0.5 and then add them together. So why might this be a good idea? Like, you might have thought, oh, well, why don't I just, like take an average between these two, between the non-linear path and the linear path? I think that's an intuitive idea. Why might you think that you need to do that? But what's the problem that probably gets introduced? Yeah.
Well, wouldn't it be training it if you left it out? It would be figuring out which is contributing more to the following layer if you left the 0.5 out. Like, if that doesn't make sense, then you can just
I'm not quite sure what you're saying.
Try
again.
not sure. I think.
See if you can.
I think maybe I'm confused. You can go ahead. Don't worry.
Okay, let's go. Go ahead.
0.5 would introduce like a derivative of the same one.
Yeah, okay, so that's a problem. So you identified a problem. I mean, I've already told you what to look for, but now you see it here. You say, well, this 0.5 here, that seems problematic because as stuff propagates back, it's going to get multiplied by 0.5 every time, and it feels like vanishing gradient. Okay. You might think that this is necessary, I don't know, conservation of something, like instead of, like maybe it feels weird to be always adding something, like we're always adding, it's going to get bigger and bigger and bigger, and so maybe we want to take an average so it sort of keeps things the same norm, something like that. But it turns out it's a bad idea. So the story is You double your error if you do this. Okay, and notice, if I build a 110 layer ResNet with blocks that look like this versus blocks that look like this, which one has more parameters? Same number of parameters. So why is this error so much worse? Do you think it's representation, generalization, or trainability? I'm guessing trainability. Okay, same number of parameters. Okay, so you say, well, what about this? So let's see what this guy is doing. This is called a highway network, so, or similar to. So here you have the nonlinear path, and you do this one-by-one convolution, followed by a sigmoid, a 1 minus, and a times. So this is, so you've got the sigmoid coming out of here, and then 1 minus the sigmoid here. So what is this doing? Interpolation. But the interpolation is learned. It gets to pick. So this says always take half of each one. And you might say, well, let's generalize that. Maybe sometimes I want to take 80% of one and 20% of one, or 20% of one and 80% of the other. And how do I know what number to put there? I don't know, but I'm a learning guy, so let's parameterize it. So this, so this says this little block is learning. It's going through a sigmoid, so it's always going to be between 0 and 1. And so it's learning, should I take the identity or should I take the nonlinear path? Which one do I care about more? And what, so does this have more parameters, fewer parameters, or same? More parameters. So this might work better because representational ability. More parameters, generally more representation, but what happens? Error's higher. So why is that? Probably trainability. Probably this, like you're introducing something weird here, that clean gradient flow backwards doesn't exist. Okay, hopefully you're starting to see a pattern. How about this shortcut only gate? So this is like a slightly chopped down version of this one. It's just missing this extra multiply over here. What happens? Terrible idea. Don't do that. 12.9% error. What about this one, where you like maybe just scale something here directly? What about that? Don't do that. Terrible idea. What if we drop things out, maybe, right here? That's an awful idea. Okay, don't do that. Okay, so it really sort of feels like, I think you can summarize this slide as saying like, don't mess with the identity path. Like anything you do to it is almost certainly going to be worse.
But we're still leaving the ReLU.
Oh, we're still leaving the ReLU in there. Right. Okay, so I think there's a slide on this. Let's see. Okay, so the after mapping, right? That's what we'd like to know. So, okay, here's the original ResNet. So it goes through, we have the addition, the ReLU, and then the next layer. Here, you put a batch norm in, and here, you put the batch norm kind of over here, but you leave this perfectly, I guess, linear path. And so let's see what happens. So this is showing batch norm plus the ReLU, and just the ReLU. So what's the conclusion here? 0. So yeah, so the batch norm thing, that was a bad idea. So putting the batch norm in this identity path, don't do that. What about adding the identity? Or getting rid of the ReLU, what happens? It's better. So they actually made a mistake. They're saying, like, when we first introduced the ResNet, we thought we needed this extra ReLU, but actually, that was messing with the identity path. Don't mess with the identity path. So you get even better results. Besides, wait, this is now 1,000 layers. You get an even better result if you get rid of that ReLU right there and just leave this in here. Okay, I think this is just fantastic work because I think they've really ask all these questions. Oh, and so yeah, so you can start adding things, some batch norms, and you can kind of do whatever you want over here. So that's okay. So they've got batch norm ReLU weight, batch norm ReLU weight, and then it gets added. All that's fine. But don't mess with the identity. There's some more comparisons. So error rate, method. So these are all of the competing networks. This is network in network. I forget what all these are. Highway network. 110 layer ResNet, 1200 layer ResNet. And then they use this pre-activation thing with the batch norms. And you can see that, of course, I mean, you know, if you don't write papers unless you get to put your method here in bold, you're doing better than anybody else. So, of course, according to, but this is super influential work because no one had been able to train a 100-layer network, much less a 1,000-layer network. Okay, more ImageNet experiments. So here, ImageNet is bigger. So again, sort of this pre-activation thing, 200 net.